My name is Jason Xu. I'm a statistician. I have a stats PhD, and I did my postdoc here at UCLA in biomath. I actually don't do a lot of genomics work yet, but I just started coming to CGSI. This is my second time, and I'm more of a methodologist. I come up with algorithms for statistical and machine learning, and would like to find new applications, and I think genomics is a great one. In fact, some of what I'll talk about today and what I'll shout out is other people at UCLA who have used some of these methods. I'm currently at Duke University and moving to UCLA next year, which is really exciting. So today I'll talk a little bit. So last year I gave a talk related to something different. If some of you might, I think I've recognized some familiar faces, and that was on how to incorporate constraints and things such as sparsity into general problems. And I realized it was maybe a little too technical because this is such a broad program. There are people here who are probably more technical than me, and there are also people here who are more on the wet lab side. And so today, I can only talk about things that are a little bit mathematical, but I want to focus on what I think is one of the simplest, but sort of one of the most persistent tools in machine learning and statistical analysis, which is k-means for the canonical unsupervised problem of clustering. And in particular, k-means has been around for about 100 years, or maybe 60 years, but we are trying to do things that take that algorithm and overcome some of its shortcomings, but without making it too complicated so that you need to know a lot about, have a PhD in a quantitative science to understand. So I'll go ahead and get started then. So what do I mean by k-means, in case you have not encountered this problem? It's basically a way to discover groups in your data, right? So it's called unsupervised learning, which simply means that you are just looking at the data and trying to group them. There's not like also labels, which would be supervised learning, okay? So let's say you have n data points, and they're measured in some space. So you might have n patients, and then d sort of measurements, whether they're gene expression or something else. And so they live in d-dimensional space. And your goal is to think, well, if there are maybe k groups among the data, how do I discover that? How do I separate them into k groups? And k-means is a pretty natural way to do so. It poses the problem by saying, well, let's say that there are k centers or centroids, right? So this lives in the same space as the data, which might be d-dimensional Euclidean space, but there are only k of them instead of n, which is the number of data points. So to try to naturally do this clustering problem, sort of the objective here, is written in sort of an equation, but really what we want to minimize is some measure of fit, and that happens to be Euclidean distance here, and you want to do so by minimizing that loss within clusters. So you can think about this as minimizing a criterion called the within cluster sum of squares. And indeed, it's looking at the distance between my data points and each center. And I'm trying to decide which partitions they belong in so that the distance is minimal over summing over all the centers. Right, so there's different ways to write this. Some people might think this is a little simpler. Which is to look for the best way to partition my data, which is this general C here, into different clusters so that the cluster variance, or the within cluster sum of squares, is minimal, right? Okay, so that's the objective, and you may have heard of k-means. Even if you haven't studied this, you might have even just used a k-means routine in Python or something like that. So most people would solve this using a pretty simple algorithm that goes back to the 50s called Lloyd's algorithm. Right, so Lloyd, in fact, this is so prevalent that some people, when they say k-means, they refer to this algorithm. But I have to make this distinction because we came up with a different algorithm. K-means is this problem, right? It's the problem of solving this, which is actually, mathematically is NP hard. So it's a combinatorially hard problem because I have to sort of think about all the subsets I could partition my data into. Lloyd's algorithm is the sort of iterative way we would try to get a solution to this problem. And it's not a perfect algorithm, but it is a very simple one that I think there's been hundreds, thousands of papers tackling the same problem, and some of them outperform in different ways, but this is probably still the most widely used, one of the most popular. Probably owing to its simplicity, we see that we want to minimize this objective, and even if you didn't derive the algorithm, I would say that the steps are quite intuitive. If you have a current estimate of all the class labels, so each data point is assigned to some cluster J for now, then to update the center of that cluster, you would just take the average of all the positions of your current points assigned to that cluster. Okay? And now, now that you've updated the centers, maybe some points are now closest to a different center. So you are going to update their memberships by updating everyone's label by the current closest center. So does this make sense? I'm getting some nods, right? So you have a bunch of data, like right now they're all closest to some point on the left, and then now the center, as you might expect, is just the average of their positions, but now some of the labels might have changed, right? And you keep doing this until the algorithm stabilizes. Well, people use this all the time, but it has some drawbacks, and I'm just going to give you a sense of that via this one picture. So this is a pretty simple problem in the sense that it's only two-dimensional, right? I generated data in 2 dimensions, and moreover, they're nice clusters. They're kind of these nice spherical things. None of them are really imbalanced, which are problems you encounter in real life. And yet, even in this ideal setting, there are k equals 50 true clusters among all the data. It's thousands of data points. And when I run k-means, this is one example solution. And I've even drawn the cells to just make it easier to visualize. But I would say that it's made some clear errors, right? Like this cluster is clearly just as clear of a cluster in some subjective sense as this one. But the algorithm has put 2 centers here, so it's split that cluster into 2. Right? On the other hand, sometimes you'll have 2 clusters that are sort of obviously different memberships being partitioned into the same cell. You might even have some clusters split into 3. And this happens all the time because, like I said, this objective function is actually very hard to optimize perfectly. And this is simply one greedy algorithm that tries to get an approximate solution. Okay? So this is the problem motivation. So the first part of this talk, by far the longer part, is one of the works we did just a couple of years ago on how to avoid this problem, right? Because if we solve for the global solution, if we really optimize this objective, we would, especially in an ideal setting, you'd expect to get it perfectly. But what's happening is because the objective you're trying to optimize has a lot of sort of little traps, has a lot of local minima, you can get stuck at a solution like this which just does not look right. So this will be the part that, it has a little bit of methodology, and I want to show you behind the hood how you can try to modify these simple iterative algorithms, with some ideas that take a little more machinery, but in the end, retain an algorithm that's almost just as simple. In fact, in terms of computational complexity, is just as simple. So, right, like I said, the objective is non-convex, and what that means in practice is that the algorithm, that simple 2-step alternation, will be sensitive to the initialization, right? You start it somewhere, and it'll converge somewhere, but where it converges to will depend very highly on where you start. And this thing becomes worse in a lot of real settings. For instance, when you have a lot of features rather than just 2 dimensions. And also, when Euclidean distance might not be a good measure because things aren't very spherical or balanced. In particular, like I said, this comes from the fact that you actually have a very hard math problem lurking. And the way that people deal with this is largely dominated by sort of what I would call external improvements. So what I mean is they're still using this 2-step algorithm at its core, but they might do things like have a clever way to choose good initializations and then take the best of many random restarts. So this is always a great idea, and we should be doing this. But one of our methods is to try to complement this, right? Because if you have these clever external things, like taking the best of random restarts and having good initializations, you could do even better if you also improve the algorithm that wraps around, right? And so this is where we come up with a new iterative algorithm. Like I said, our goal is to try to retain the simplicity of Lloyd's algorithm because nobody asked for another k-means algorithm. And the way we do this is actually using majorization minimization. So if those of you who were here yesterday, which, I just flew in yesterday, but Ken Lange gave a tutorial on majorization minimization, which I'll review very briefly here too, so it's self-contained. And I wanted to show you kind of at least the use case, the ideas behind how that sort of perspective on optimization can help us overcome this sort of persistent problem of local minima. Okay? Great. Okay, so the point of departure is actually an algorithm that goes back a long time ago. This was an attempt by some researchers at IBM Research that were tackling the same thing. They noticed, of course, k-means is very sensitive to initializations, and the objective is non-convex. And the objective involves the min function somewhere, right? I wrote it as you're only counting the distances to the closest center, which is where the min comes in, right? I look at all the cluster centers and I'm counting the contribution to the closest one. So because the min function is pointy and non-convex, in terms of the argument theta, they made this observation that, well, the harmonic mean is a nicer function, but kind of behaves like the min function. So this plot is from their paper, and they're saying, well, the shapes of these are quite similar. And so if I just swap out the min in that objective, here was a min from 1 to k, min over j from 1 to k of this, they're replacing that by the harmonic mean. And they're thinking, well, this might be easier from an optimization perspective, but still have a similar behavior. And it worked to some extent, but the problem is it quickly deteriorates as soon as you move beyond 2 or 3 dimensions. So this picture does not at all resemble this picture in higher dimensions. Basically, the volume is totally different. But it was still a really neat idea, we thought. And also the paper is kind of heuristic. It didn't really come from a particular recipe for coming up with optimization algorithms. So what we noticed was, well, the harmonic mean is simply one member of a general family of nice mathematical functions called power means. Okay? So the class of power means is well studied. Kolmogorov was interested in these things and proved a lot of cool if and only if statements on how, for instance, he proved that it's the only class of functions that satisfies all these properties. I'm not going to deal with too much of the properties here, but I want to highlight a couple, which is it's well known that if I take the limit of this power here, right? So this is some kind of, it looks like an LP norm, for instance. If I take this power and send it down to negative infinity, I recover the min. And if I send it to infinity, I recover the max. So I have a bunch of numbers, z1 through zk. So this power mean for s equals infinity is like taking the maximum element and taking the minimum element for negative infinity. There's also a nice inequality which will play a big role in using the MM principle to derive an optimization algorithm. Okay? But yeah, we basically notice, well, the harmonic mean is just a special case of this. And so are things like the usual means we have, like the normal arithmetic mean. And also there's a connection to the min function, which shows up in the k-means original objective. So can we generalize that sort of nice idea behind k-harmonic means, but make it actually work beyond sort of simple settings? Right. So if this is, and I'm just copying the power mean formula here. K-harmonic means in terms of replacing the arguments by, the things that happen in clustering objectives, right? So each zi is now the difference between xi and the clusters j. In k-means, it's the minimum over the closest j, or the minimum that chooses the closest j. Otherwise, in k-harmonic means, it takes the harmonic mean over all the j's. But there's a continuum of other power means in between these. And the idea is to try to use those. So what I plotted is actually a very trivial case. It's kind of a funny plot, but if I'm clustering in one dimension, but I'm plotting the objective as the location of the centers change. And there are 3 centers, so there should be a 3-dimensional domain, but I'm plotting a cross-section. The point is, this is some objective function, and this is the k-means objective function, and it's got a lot of peaks and valleys that your optimization algorithm might get stuck in. However, if you try to use this class of power means, indeed we see that if I used s equals -1, the harmonic mean, that objective is much nicer, just like they claimed in that paper. And if I even, far from negative infinity, if I have -10 for a low dimensional problem, it looks pretty much just like negative infinity, the original objective. However, and I can keep changing the powers and get it to be smoother and smoother. And of course, between -1 and -10, it would become gradually rougher and rougher. So our idea was, well, rather than getting trapped early on as your algorithm is trying to find the optimum, what if we start with those smoother objectives and gradually decrease toward the original target of interest, which is the k-means objective. So you're just sending that power lower toward negative infinity throughout an iterative scheme. Okay? That's the kind of big idea. And then I'm going to give a little bit of detail on how MM algorithms are used to come up with such an algorithm that lets us do this. Right? So the simple idea is use a sequence of objectives that are progressively rougher, so that as the algorithm's learning first, it's kind of moving the right way without getting trapped. And then at the end of the day, it's still going to hopefully target the original measure, right? As you might expect, if I was only using this the entire time without this kind of annealing behavior, well, the location of the optimizer might be different than the location of this one. But if I run this algorithm, then I'm still targeting the k-means objective, but avoiding the local minima. Okay. So a little bit of review on MM. And you were lucky to hear this from Ken Lange, right? It's not just like, oh, Ken is the local expert on MM. He's kind of the horse in the proverbial straight from the horse's mouth. So he really came up with a lot of this stuff and has written the book on it. But I'll do my impression. So in MM, the idea is you have a function, the k-means objective in this case, that's difficult to deal with. And instead, you want to transfer that difficulty into an iterative procedure, a sequence of simpler problems. And you need those surrogates in that procedure to satisfy two conditions. Don't need to get too technical, but I'm going to show you the picture. Okay? So if this is maybe some unknown, really hard objective, which doesn't look that way from what I plotted, Ken might have shown you this graphic too. In an iterative algorithm, you would exhibit a surrogate function, which requires some math, but if you can derive a family of surrogates that's valid, you want to do so such that this is easy to optimize, right? Finding the minimum of this easy problem will give you your next guess, and then you continue doing this and it'll climb downhill in minimization, and similarly it'll climb uphill in maximization. Okay, so these things work that way. And so how will it work in our problem? Right, the sort of overall objective is a power mean, right? It's going to get more complicated because rather than, these z's, remember, are going to be like norms of x's minus thetas, and the real problem is in theta. But let's just think about the geometry of the overall power mean. So you can look at the gradient and the Hessian and show that as long as s is less than or equal to 1, which is the entire range we're operating in, it'll be concave. And this picture shows generally a concave, it's always true that a concave function is at a point is dominated by or majorized by its tangent plane, right? It's kind of, even if you define, like if you take a class in convex analysis, the definition of convexity is that, the sort of supporting tangents, the tangents support it. So concave, this is basically the definition, right? If it's concave, the tangent line or tangent plane in a multidimensional space is always going to sit above the function. And so that means that, the first order Taylor representation where I use only the first derivative, this is the equation of the tangent plane, is sitting above the function. So this is a useful observation for me because I don't know how to optimize the power mean sort of directly when it's in terms of theta, right? If I write this in terms of theta, I actually would not know how to optimize this at every step. But when I have that linear representation and I had an iterative algorithm, these first terms come out as a constant because they're just plugging in the mth iteration. And the thing I optimize is something that I can deal with. Okay? So basically, G is the whole tangent plane, but when I take derivatives with respect to theta, the complicated stuff drops out in an iterative scheme. And you don't have to follow all the math. The idea is, from the MM perspective, you can check that using simple calculus gets you a closed form minimizer for those surrogates. Okay? So you would think, again, it's like the equation of a line is trivial, but it's that wrapped around thetas, right? This is the picture for z, but z is a function of theta, and yet theta can be solved for in closed form. Okay? So that's the rough idea. You don't need to worry about too much of the details, but we're able to derive an MM algorithm for each power mean. So at the end of the day, when I have this representation for theta, my algorithm ends up being, I compute the thing, the first derivatives that define my surrogate, which is easy, and then I also plug it in to update my centers. So at the end of the day, it very much resembles Lloyd's algorithm, because Lloyd's algorithm was about updating class assignments, which is looking for the closest centers, and then re-averaging to define the center averages. Here, I'm updating sort of weights, which are just like updating class assignments, but they're weights instead of hard assignments. And then I'm updating the centers via an averaging step, but it's a weighted average depending on those weights that come out as derivatives. Okay, so you might not have understood all the details of MM, but you see how the geometry comes in, I hope, which is you need to make use of this to kind of know how to come up with G's, but then it reduces the problem to simple calculus. And the nice thing is that in solving that problem, your algorithm ends up being basically a two-step algorithm. The only thing you have to do is also decrement S to make the annealing happen, to make it become rougher and rougher. Yes, okay.
Yes, sir. So, let me understand. First, how did you obtain the convexity? What approximation did you obtain the convexity? And then, so you have every single step here is closed form, or polynomial or whatever, but jointly you sort of end by hill climbing. Is that correct?
Yes, exactly. Great question. So first, the convexity is a natural, we just show it. So it's like you know what the formula for a power mean is, And then you just check by taking, you derive its Hessian, and you see that as long as S is less than 1, it will be concave. So we do not assume anything about convexity. Rather, the power mean itself is by nature convex or concave, right? And then for your other question, indeed, it's not like all of a sudden we can solve the problem in closed form. Each surrogate, each of the G's is solvable in closed form. But like you said, each of them is only one update. It's almost like if I came up with a gradient descent algorithm, I'd like, hopefully, to be able to compute the gradients rather than solving each stationarity equation by bisection, right, or root finding. So this is simply saying that each problem in the sequence of problems is really easy to solve. But of course, we did have to convert a hard problem into a sequence. And luckily in this case, so the other thing about MM, I'm not really talking about MM here, is the algorithm works as hill climbing, but it could be garbage depending on how kind of tight your surrogate is. If your surrogate is tightly hugging your objective, then this thing will happen in just a couple steps. Otherwise, you could be making really painful, slow progress. And we've absolutely seen both. But in this problem, it seems that these surrogates work really well. Yeah, so great question. Yeah. Okay, I still have some time, so let's go on. I'm hiding most of the proofs, but certainly we can show that it's like an MM algorithm. It converges monotonically to the objectives we care about. So yeah, the main punchline is this really does look as simple as k-means, but we're doing a lot of geometric stuff under the hood. And the only thing you have to do is change a number and make it smaller, however you choose. I will say that this is the part that is least rigorous, so that's the part we want to do more analysis on. But the nice thing is that we see that it's not it's not like you have to get this just right. You can do a lot of things here, like choose how to decrement it, and they might perform differently in speed, but they're all much better than k-means. Okay. So, like we said, it's meant to resemble the simplicity of Lloyd's algorithm, but also formally, it has the same time complexity. It's nice that the updates are always a convex combination of the data points, because what that means is in terms of not just the objective function, but the parameter space, you're staying within the convex hull of the data. So you're never going to get something that's kind of shooting off in a way that doesn't make sense. And then, of course, it's nice because it's satisfying to completely generalize this algorithm in the sense that if I fix S, then I recover that algorithm, which was not derived from a more formal perspective. Great. So a couple nice properties here. I just want to show you an example. Of course, one can make the same plot just by restarting this enough, but this is just a random example. We see this all the time, which is I generated sort of a data set just running k-means, again, I would say on ideal data. These are all Gaussian clusters. They're spherical. They're pretty well separated. I wouldn't blame k-means for getting some of these wrong, because this is a slightly harder setting where these are pretty close. But it's hard to see. It's putting 3 clusters here in this one cluster. These are actually 3 clusters that may be just as hard as this, but it's calling it one cluster. So it's not the easiest. It's not as trivial as my first problem. But power k-means is doing a good job. Like it found out that these are 3 different clusters, which even though they're overlapping, based on the variance, you should be able to detect in a good algorithm. And so it's not perfect, but it's doing a lot better in sort of what I would say are eyeball mistakes, right? You can tell. So that's great. And just a little more of a simulation study. I don't need to focus too much on the empirical results because you can check out the papers. I really want to focus on ideas here. But we want to kind of repeat this in many times for simple settings first, and just make it slightly harder by increasing dimension and things like that. Check a clustering metric as well as check just in terms of sheer optimization. How is this doing compared to Lloyd's algorithm targeting the same objective? And this plot is kind of visually stark in the sense that I'm actually now just plotting all the converged values over many random restarts. And this is just taking the original paper from the k-harmonic means paper, so it's a simple analysis for dimension 2. And even in that setting, we see that ours is kind of consistently reaching a low objective in the minimization problem. Other methods, there's all sorts, right? Of course, taking the best of random restarts is still a great idea, but we're cutting down on the variability to initialization by quite a bit, as you can see visually. Excuse me, and then the performance comparison here, we actually see that indeed, over different dimensions, it can be sensitive, for instance, to the initial value of that power S. What's not even shown here is, of course, it will also be sensitive to how quickly we decrease S. But here, we're using a very simple rule on how to decrease S. I don't even remember, it's like multiplying it by a number. And the thing is, even though the performance in a given dimension depends on the choice of S, regardless of how you chose that tuning parameter, it's doing better than the competitors. So the message here is that it's sensitive to tuning in a sense, but tuning it only just improves the amount of gains you get, whereas it's not too sensitive to tuning in the sense that it's not failing when you don't tune it right. It simply can do even better. Right? So that's kind of nice. We see that under variation of information as well as other measures like adjusted rand index, and in this case, the quality ratio in terms of the optimization objectives here. So I'm going to skip over these. These are in the paper, right? But it's performing really well on sort of standard simulation studies that we took from the previous papers just for a conservative comparison. Great. Okay. So just a couple of remarks, right? So the original k-harmonic means algorithm, we saw that it degrades rapidly as the dimension increases. This is kind of what motivated us to come up with this algorithm. And of course, if you decrease the initial S, then the gains are kind of vanishing because you're basically starting the objective to look like k-means. But otherwise, when you make it harder by increasing the dimension or something like that, it's retaining the success of the other ones when they start to deteriorate. And it's also fast, right? It's fast on kind of big sort of classic benchmarks. So I'll give a little summary before talking about the other idea, which is a much briefer part of the presentation, right? So this is one example of how a simple iterative algorithm coming from MM is really improving sort of directly a classic algorithm that has persisted because of its own simplicity, right? We saw that there were some good attempts to improve the algorithm itself, but they were confined to low dimensions. So this generalizes those benefits, which lets us take the best of both worlds, because when people abandoned these ideas in the 2000s, what really took off is this alternative approach, which is clever seeding, right? If I can't improve k-means, I can do better initializations, I can think about the best of initializations. Well, now we can do both. And of course, because it's simple, it's not too bad to extend this to do things like feature weighing, to do kernel clustering, and to do clustering for Bregman distances or exponential family data. So we've done some of those things. We can show optimization, but we don't have a lot of results, even though I'm a statistician, on sort of things like consistency statistical analyses. And also, like I said, we don't know things about like how to optimally decrease that annealing schedule. So that's sort of an empirical thing still. So that would be a great thing to analyze and understand for any mathematicians in the audience. And of course, the nice thing about this, especially for real scientists like many of yourselves, is clustering is often just a subroutine in something bigger that you're trying to do, which is why we emphasize the simplicity, right? There's tons of statisticians that work on clustering, but their methods might be so complex that a comp biologist will not want to put it within just like just one step in a pipeline. Right, so I'd encourage you to check this out or maybe even work on it. I think it's a neat project that was really fun and kind of came out of collaborations here at UCLA. Like I said, the second part of this is going to be briefer, and it's even simpler in the sense that it didn't even come from MM or anything. It's just really coming from observing k-means and thinking about what could go wrong. So I like this because I like elementary things that are elementary to state. So the thing here that we're trying to tackle now is that, well, when your data live in D dimensions or P dimensions or whatever you want to call it, if some of those features are uninformative, noisy features, as you might say, even in a non-math setting, that can confuse your algorithm, right? So this is one of the simplest examples taken from a classic paper, which is, you have these two clusters, very obvious to the eye how to cluster them. If I run k-means though, it's cutting them this way. It's thinking that somehow maybe it's putting a cluster center here and a cluster center here or something, which makes sense because of the tilt. But then your classification is wrong, right? So the objective led you to do this. Whereas if you told the algorithm, look, the information that distinguishes them is along this axis, but this axis is noise, right? They look identical from this perspective. If I now cluster only along this variable, then of course it's not hard and you get it right. Okay? So that's a very simple, obviously this becomes much worse when you have thousands of features, which has motivated people to do something quite natural and simple, which is to look for sparse solutions, right? What if I can cluster along only a sparse subset of features? In this case, reducing the dimension from 2 to 1, but sometimes you might want to reduce it from 10,000 to 50, right? And so this is actually, that figure is from Witten's paper here. And I'm not going to go into the details, right? This is just to show you what people might do. So they rewrote the within cluster sum of squares thing. Instead of minimizing within cluster sum of squares, you can write it equivalently as maximizing between cluster sum of squares. So these D's, just think of them as those square distances we had. I'm not actually going to go over this method. I just want to show you, you end up with a constrained optimization problem. You get these weights that are what you are going to incorporate sparsity on by using penalization ideas from statistics. And the problem is, this is already maybe too much for people that don't do math at all. And we want these tools to maintain their simplicity and be accessible. So I actually really like this work, and I have other work that builds on this, right? But instead, if you don't want to do things like have this algorithm that ends up using k-means as just a subroutine and then having even more complicated things to optimize the weights, right? When I look at their algorithm, I need to know a lot of things. I need to know what a proximal operator is. I need to know about like L1 or convex penalization as a proxy for sparse problems, and I need to trust all the stuff there. I need to have embedded optimization problems. And even at the end of the day, this can improve your performance a lot by weighing down the noisy features. But in many cases, you don't get a sparse solution. Basically, all your weights are positive. And a practitioner really wants to interpret maybe that here are the genes I select and here are the genes that don't matter, right? So what did we do instead? I hope you'll believe that this is a simple observation, right? Just revisiting the original stated goal. We want to do k-means clustering, but we want to only do so on a subset of relevant features or dimensions among RD. So you have these centers, theta 1 through theta k. You have k centers you're looking for. But if I believe that only s of the p dimensions are relevant, then these clusters only need to differ among those s features. Right? So if you go back to this picture, right, like these cluster centers might as well both be 0 along the y-axis because there's no information along the y-axis. Along the x-axis, they should be in different places. So along the s dimensions that matter, they should be in different places. And among the other p minus s, well, those things are just shared information along the clusters. They don't drive the clusters, and therefore they should have the same value for that jth component of their cluster center. So I claim that that's a pretty simple observation that we might posit as a goal. And I'm just assuming I'm going to call that mean 0 without loss of generality, right? They could be all centered at 5, they could be all centered at whatever, but we're going to say that among the non-relevant features, they're centered at 0. So we can just try to slightly modify k-means. We know that k-means is doing two things. It's recomputing averages and then assigning to the closest means. So all we need to do is say, well, how do we define those centers? We want to only define them using the S relevant features because the P minus S, which might be large, is adding a bunch of noise, right? You can't estimate it. They're in different places. The slightly different places they put can really drag away your overall mean squared error and sort of confuse your clustering algorithm. So naturally, we need a way to figure out, well, what are the S most descriptive features? And this shouldn't be too hard because we know that there's contributions to the overall objective. The overall objective is a sum over I and j, right? However you want to write it, whether you want to write it in this way or in the way I've written in the beginning. And so if I only look at the contribution among the Lth feature, so L going, I guess I called it j before, but if I'm looking at the features, so L is going from 1 to p, I'm only going to fix 1, and I want to look at the contribution to the objective. And don't worry about the math. When I just look at these simple sums of squares, I end up with an expression that does not depend on I. So basically, I can sum up the data, and I can just look at these features so that the whole point of this slide is just to say that I can compute these scores on which features are relevant without taking an extra pass through the data. I can just look at the current centers and assignments and just rank all the features because this is their score. So if I have k-means, which gives me assignments and gives me centers, all I have to do is use this formula to determine the ranking of the features, and then I just take the top S. So if it's so easy to detect the features, then I have a very, very simple algorithm that modifies Lloyd's algorithm, which is just average according to Lloyd's algorithm. Of course, you can also save time, because if you only have S features, if you average over the ones that are all the same center, they're going to stay the same. So I'm going to assign the cluster, I'm focusing on the wrong step. The cluster labels are still just whatever is the closest center. And of course, I can save time here too, because a lot of the components are the same, so I can ignore them. They're all going to be closest along the P minus S features. In between the assignment step and the center step, I'm going to sort the top features, which might have changed, and I'm going to keep only the top S. And then I'm also going to just re-average all the centers. Again, I might as well only do this for S because the rest of them are the same. They're all 0, so they don't affect the average. So I basically have Lloyd's algorithm, but with fewer things to sum over in each step, fewer things to check in this step, fewer things to add in the average. And in between, I have to possibly re-rank the features that are contributing, that are driving the clustering. In doing so, so far I have no theory. We proved some things about this, but nothing deep in the paper. But it ends up being like Lloyd's algorithm, but kind of does feature selection. So when we look at the results, I made a simple simulation where there are only 10 true informative features, and the overall number of features is increasing. So basically, as your feature dimension increases, but more and more are noisy, they're just going to confuse k-means. And we do see that. We see that k-means is doing worse and worse here. Here, you can trust this because we're not doing better than our competitors. The sparse k-means algorithm is doing about as well in terms of this measure and other measures we checked. The difference is our algorithm is way faster, way simpler, right? We didn't derive it from a bunch of sort of PhD level stuff. We just kind of made an observation and stuck one step in the middle, which is sorting. So it's way faster, but what's not seen here too is that in many of these cases, sparse k-means comes up with no 0 weights. So it's not really sparse. It just weighed the features to get good clustering performance, just as good as ours. But if you care about interpreting the features, we actually zero out all the right ones. So it has a sort of 0 false negative rate, false discovery rate. And also, we don't need to tune, if you know that there are 10 features, then you can just rank the top 10 at every step. You don't need to carefully tune all the weights in something like a penalized approach. Okay, I'm going to skip this quickly, but I just want to say that to tune our algorithm, like I said, you can directly put a desired sparsity level because it's interpretable in ours. But if you don't know S, if you don't know what the sparsity level should be, you don't know how many relevant features are driving your clustering, you can use the same things that people tune other methods with to tune S. So you might usually call this lambda in a penalized approach, but you can use things like the gap statistic, which is kind of looking at a null, which is like what would happen if I just permuted all the features sort of independently and look at the difference between how we're doing and sort of that null. So this is a heuristic that people use in clustering. It works just as well for us. That's the goal here. And you can see more examples in the paper. But in the real data benchmarks we saw, it pretty much outperformed all the sort of comparably simple peer methods and the sort of canonical method that's much more complicated, except on one data set, in which case an entropy-weighted approach outperformed this. So that's this method. I want to just discuss a little bit and keep some time for questions. So, our algorithm here is only performing about on par with kind of what people use in statistics for sparse clustering. But the gains here are, it's much, much simpler algorithm. And as a result, it's faster. When you know the sparsity level you want, you don't even need to tune anything. Otherwise, you can tune it for the same using the same methods that people have done for the others. Something I didn't talk about today, but it also doesn't bias estimates of the centers toward the origin because it doesn't use something like a shrinkage penalty. Like I said, especially for this audience, because we think that this is just as simple as k-means, it's going to be easier to incorporate within sort of more complex pipelines you might use for your science. And this is a paper that came out of UCLA as well. I'm not on this paper, but some researchers here did apply this exact algorithm for doing some admixture estimation at biobank scale, right? So a lot of times you don't want to use the complicated optimization methods, which I'm also fond of, on real problems that are huge. In this case, if you're doing admixture estimation, some people might first identify using all sorts of various clever machine learning tools or biological knowledge, like which SNPs are informative, and then they'll just run their algorithm on those. Well, this method will allow you to sort of jointly do this, right? As you learn from a likelihood on your admixture, you might also realize that actually your initial set of SNPs is not the most informative for that likelihood, but a different set are. And so they're actually running this under the hood to select sort of adaptively which ones might be interested informative. And they're able to do it at scale because of how easy it is, how simple this algorithm is to embed into a larger one. So I'll just leave it at that, and thank you for your time. A couple references here. These are really the two I talked about. This is one of our own works that uses a little bit more advanced stuff to do both, to use power means but penalize that. But so far I've talked about two separate ideas that both improve upon a simple algorithm, and the main goal is that we see real gains, but we've really retained the simplicity of that original algorithm. And we think that the simple algorithms are the ones that persist. This is the other thing I just mentioned on the last slide that's kind of relevant to a lot of people's interests here, which is really using this for sort of a genomics application. So thank you.